That's about it. I think it's we can get going. 26 people.
Okay. Very good evening, everyone, and welcome all to the sixth lecture series in this monthly research article spotlights. So the today lecture is by Dr. Bijesh Malla. He completed his bachelor's from Utkal University and master's from the IIT Nagpur, and he recently completed his PhD from Chemistry Department IIT Madras. The topic he will present today is about the growth of Clathrate hydrates in nanoscale ice film observed using electron diffraction and infrared spectroscopy. So over to you, Bijesh. Please make sure you are completing on time, and there should be time for the discussion. So over to you.
Okay, thank you. Am I audible?
Yes, you are audible.
Thank you, Deepak. Okay, let me share this screen. Okay, I hope my screen is visible.
But not in full
turning
screen
up
mode.
videos for better clarity of
It's full
voice.
screen.
Okay. Just 1 minute for.
Is it recorded now or going on? And recording is going on?
Yes, sir, it's recording.
Yes, fantastic. Thank you very much.
Just once the slide. Okay, just 1 minute while this slide is not. Let me see if I can.
You reshare and then run it.
Yes, yes. Not going to next slide. The problem is this slide is not going to next slide.
You share the all screen.
Yeah. Now it is working. Okay. Thank you. So, good evening, everyone. Today, I'll be discussing about one of my paper, which is published recently in JPCL, whose title is Growth of Clathrate Hydrates in Nanoscale Ice Film Observed Using Electron Diffraction and Infrared Spectroscopy. So this is a collaboration work between IIT Madras and University of Houston. This is the TOC which you are seeing is representing the title. The detection of clathrate hydrate by using READ, reflection high energy electron diffraction, and RAYATS, reflection absorption infrared spectroscopy. So clathrate hydrate chemistry starts when Devi encountered a solid compound which is chlorine and water complex. So before that, it was thought that this chlorine and water solid compound is nothing but a chlorine solid, pure chlorine solid. But Devi identified that as a gas hydrate. He's the person who coined the term gas hydrate in 1810. So, but that time it was not known, like the molecular composition of this gas hydrate is not known. Later, Faraday told that this is 1:10 ratio of chlorine and water. Later in the decades, from 1897 to 1920, people have created different kind of gas hydrates like hydrocarbons, halogens, and different organic molecules. And the composition that time was suggested its gas is to 6 water. After 1912, when X-ray diffraction was evolved by Braggs and Lau, they have diffracted various different crystals. During that time, after like 1951, von Stuckerberg identified the structure of methyl chloride clathrate hydrate, which is cubic structure 1 and structure 2. There he told that the clathrate hydrate cages, which was thought it's 6 water molecule, it was pentagonal dodecahedron. It's 512 of water cages. And later, both von Stuckerberg and Muller identified another structure, which is hexagonal structure. So in today's date, if you'll see, there is 3 known structure, 2 cubic structure and 1 hexagonal structure. If you take as example of cubic structure, it has a definite number of cages like 2 512 cages and 6 512 62 cages. So in this cages, water cages, the guest molecule is encapsulated. So if you want to see, like, just 1 second. If you look at this video, this is the physical appearance of clathrate hydrate. It is resembling to ice. This is methane clathrate hydrate. When water cages dissociate at room temperature pressure conditions, methane gas is coming out from the cages, and that due to this region you can see a burning here. So this hydrate are formed in high pressure region. If you look at this pressure temperature diagram, this is the hydrate formation region. It required more than 2.5 megapascal at 273 Kelvin. This is the temperature pressure diagram from methane clathrate hydrate. And it is like the more than 6.4 trillion tons of methane hydrate is stored in the seabed. And many of their known hydrate deposit and many are the infrared hydrate deposit. But the interesting things come when people thought that these clathrate hydrates are in interstellar space where the temperature and pressure is very, very low. So before that, it is used form in high pressure, and the temperature is like 273 Kelvin. But the temperature pressure in the space is very low. Like the pressure is approximately less than 10 to the minus 10 millibar, and the temperature is 10 Kelvin to 100 Kelvin. So this is a Comet 67P. When European Space Agency observed the outgassing pattern by Rosina, which is Rosetta orbital spectrometer for ion and neutron molecules. So what they observed, the outgassing pattern of the volatiles, which is methane and ethane, is not matching with the pure desertion of this molecule. If you look at the pure desertion curve, it is here, CH4 ice, but CH4 clathrate hydrate is here. Like this, you can see it here. So they suggest that on the surface of this Comet 67P, there are hydrate deposition are there in terms of methane, ethane, and carbon dioxide. So this hydrate observed in the space, but it has not formed in laboratory experiment. It is very important to prove that, okay, this hydrate is also formed in the laboratory experiment to encounter this observation. So first, before going to clathrate hydrate, we have to see what happened to pure water ice. If you deposit water ice at 10 Kelvin, you will get a high density amorphous ice in ultra high vacuum. If you slowly anneal the ice to higher temperature, like 100 Kelvin, 150 and 200 Kelvin, this ice morphology will change. It will first go from high density amorphous ice to low density amorphous ice, followed by it will form cubic ice, then hexagonal ice. So the first experiment, the first electron diffraction experiment was done by Blake, where he showed the formation of methanol clathrate hydrate. He deposited methanol and water at liquid nitrogen temperature and then annealed to 130 Kelvin. What he saw from selected area electron diffraction, it is matching to the structure to clathrate hydrate. Then he did another experiment where he took methanol, water and carbon dioxide mixture, and he annealed to 125 Kelvin. So then he suggests that this carbon dioxide is going to the small cage of structure 1 clathrate hydrate. This paper was published in Science then, but after that, no one has tried to see this formation of clathrate hydrate in ultra high vacuum. Although Devlin has done a lot of work in vacuum conditions, but most of his works at liquid nitrogen temperature. So in 2018, our group done 2 experiments by taking 2 molecules, which is one carbon dioxide and one is methane. So Dr. Jyotirmoy has done this experiment. He deposited carbon dioxide vapor and water vapor simultaneously on ruthenium substrate. What he saw that one part of the molecules is going to amorphous ice matrix, which is 2353 centimeter inverse, but another part of the molecule is going to the small cages of structure 1 clathrate hydrate, which is 2346 centimeter. Interestingly, when he annealed from 10 Kelvin to 120 Kelvin, the peak 2353 totally vanished, and the remaining peak is 2346 centimeter inwards, which is the clathrate hydrate. So he suggests at higher temperature, all the molecule of carbon dioxide is going to the structure one small cage. But in the case of methane hydrate, it is not possible to get hydrate only by depositing the methane and water molecules. So what he did waiting at 30 Kelvin for 25 hours. After 25 hours of waiting, he saw a new peak coming at 3017 centimeter inwards, which is 8 centimeter blue shifted from the main peak, which is methane in the amorphous solid water matrix. So this blue shift referred to the molecule inside the 512 cage, which due to hindered rotation, due to the interaction with the cages and the confinement, it is showing the blue shift in case of methane clathrate hydrate. After that, our group have published many papers on different formation of different clathrate hydrates molecule like THF, dimethyl ether, acetone. But the major question was, can we see the structure of this clathrate hydrate in ultra high vacuum by a diffraction method, which is very important because we know that infrared spectroscopy can only suggest the molecular environment where it is confined or it is in the amorphous solid water and the peak shift. You can say, okay, the molecule is inside the cage with seeing the reference and some control experiment. But the diffraction experiment, the exact crystal structure remain a question. So what we did, we do the experiment, electron diffraction experiment and infrared spectroscopy both hand to hand, and show that it is possible that clathrate hydrate can form in ultra high vacuum and cryogenic condition. So the left side is our instrument here in IIT Madras, where in this particular study we have only used rare spectroscopy, which is reflection absorption infrared spectroscopy. You can see FTR spectrometer is here and here MCT detector is here. The equipment is equipped with other characterization tools like TPD, MS, low energy ion scattering, but this study is confined to the infrared spectroscopy. So another technique which we have used is reflection high energy electron diffraction. So the theory is electron will come and hit the substrate at a very low angle. Then it will go to the screen and you will see the spots. So how it worked? It worked on the reciprocal lattice. If you look at here, this is the reciprocal lattice cutting the Ewald sphere. Ewald sphere is nothing. The radius is 1 by lambda, which is the wavelength of the electron. So where the reciprocal lattice is cut by the Ewald sphere, that spot you only see in the screen. So that this distance people it's called as momentum transfer vector. So because the electron, the electron ray transferring from here to this point. So in this study, we have taken two molecules. One is tetrahydrofuran, one is 1,3-dioxylene. These two molecules form structure 2 clathrate hydrate, and it occupies the large cage of structure 2 clathrate hydrate. It is very much stable, so it is very suitable for a preliminary study of electron diffraction. So this Van der Waals radiation of THF and dioxin is 2.95 angstrom and 2.8 angstrom. You can see all the cages, different cages, average cavity radius, and how many water molecules required to form this kind of cages. With this, let's go to the data. So what we have done, we first take pure water molecule. We have deposited on HOPG substrate, which is highly oriented pyrolytic graphite. So when we see this, we saw a diffuse broad ring, which suggests a low density amorphous solid water. When we thermally anneal to 140 Kelvin, we saw a distinct Bijesh rings coming out, which suggests that it is a polycrystalline ice. So when we match the radially average electron diffraction intensity with the XRD, calculator XRD data, we have a good match with 111 plane, 220, 311 and other planes, which suggest it form a cubic ice. So then what we have done, we have taken THF and water ice mixture and we have deposited on HOPG substrate. The bright spot what you are seeing is nothing but THF crystallites, because above 95 Kelvin THF will crystalline. And this rings is suggested to low density amorphous solid water. So when we thermally anneal to 140 Kelvin, the mixture, so what we observed, the previously Bijesh ring is not visible, but a new distinct Bijesh ring is observed. When we match it with the THF structure to XRD data, we found a very good match with higher intensity like 822 plane, 400-331 plane. Along with, we have also observed a few, like a minor amount of cubic ice, which I have denoted it as has. And this is a schematic where showing the formation of pure water ice is forming cubic ice, pure amorphous solid water, low density amorphous solid water is forming cubic ice, where the mixture of water and THF is forming THF clathrate hydrate. So now, what we are doing, we are depositing on ruthenium-001 substrate, and here we have deposited HOPG. As we all know that this crystallization ice somehow dependent on the surface also. To see the surface effect of this clathrate hydrate formation, we have taken 3 different substrates. One is HOPG, one is gold 111, and one is hydrophobic surface. This hydrophobic surface formed by depositing on gold 1 octadecanthiol molecules. So you can see this is the bare substrate, and this is the diffraction intensity for the different bare substrate. This is gold 111, this is 111 plane, and this is hydrophobic surface. You can see a small distance between the 2 planes. So when we have deposited the molecule amorphous solid water and THF, we have seen this THF crystallites. You are wondering why we have seen this different kind of diffraction pattern where we are depositing THF and water ice matrix. This is due to different types of deposition. Like sometimes here in this case, particular case, THF water is a exact ratio. You can see some THF and amorphous solid water. In this case, more water molecule deposited on the surface. As you know that reed is very, very specific to the surface, few nanometer, 1 to 5 nanometer. So if we have deposited 60 nanometer, but we can only say the top surface, what is present in the top surface. So here most of the top surface is covered by THF. So you can see this kind of spectra, kind of diffraction. So, but when we anneal to 140 Kelvin, all the substrate is showing the same kind of device error, which suggests that nevertheless, which kind of surface you are using, it's a multi-layer process. So it is not dependent on the surface, and it is forming clathrate hydrate in each of the cases. So as it is a fast experiment in ultra-high vacuum, we have taken another molecule, which is 1,3-dioxylene. And similar process, we have annealed to 140 Kelvin, and we have analyzed the radially average electron diffraction intensity with the XRD calculated data, and we found a very good match. You can see it here. Then we did rare experiment, exactly the same condition in IIT Madras, where we deposited at 105 Kelvin, THF water ice matrix, THF water vapors, and here dioxylene and water vapor. So you can see at 105, different types of peaks is showing, which is amorphous solid water trapped THF. And here also you can see in one peak it is showing amorphous trapped dioxide. So this 3 different types of peaks due to the different type of interaction of THF with water ice matrix. But when we are annealing to 140 Kelvin, you can see a very sharp peak is coming out here, which is 1074 centimeter inverse, which is also well matching with the literature, which talk about the formation of THF clathrate hydrates in a single cage, which is 512-64 cage. So this is the evolution. You can see how the clathrate hydrate formation evolution is happening. You can see it started from 130 Kelvin and it's going up to 150 Kelvin. And in the case of dioxin molecule also, you can see a new peak coming at 1036 centimeter inverse at 140 Kelvin, which is due to the dioxylene clathrate hydrate. And this is the evolution. Both of this, when we compare both IR and electron diffraction, we concluded that it is forming structure 2 clathrate hydrate, where the molecules THF and 1,3-dioxylene is going to the large scale of clathrate hydrate. So we conclude like this study confirmed the formation of clathrate hydrates under UHP condition under cryogenic temperatures, as evidenced by RARES and read data. Both THF and dioxide demonstrated the formation of clathrate hydrate upon gradual thermal annealing around 140 Kelvin. So this clathrate hydrate formation was shown to be substrate independent, as we have shown in 3 different substrates. So while this study is specifically focused on 2 guest molecule, we can also expand this electron diffraction study to different molecules. With this, I acknowledge International Immersion Experience Travel Fellowship for this particular paper and CSR for this CSR for their fellowship, and Professor T. Pradeep, who sent me to the USA and who supported also financially, and Dr. Ding Sui Yang for his support in the experiment and in the analysis. Thank you all for listening. Now I'm open for the question.
Thank you. Thank you so much, Bijesh, for very interesting work and sharing with us. So since we have plenty of time, the floor is open for the discussion. So if you have any doubt, please ask.
Maybe
Shall I start?
Bijesh, yeah, Soham, you are going to ask. I just wanted Bijesh to also share as to what is going on with Clathrate hydrates now at with our cryo-EM, and what additional developments are happening with electron diffraction. This will help people to ask more questions. That is why I was asking this.
Now we are at a position to diffract different types of clathrate hydrate, as we have diffracted THF, CH4 clathrate hydrate, and pure THF also we have diffracted. And we are imaging this clathrate hydrate at atomic resolution. Although we have imaged the pure ice, cubic and hexagonal ice, but THF, CH4 clathrate hydrate we have imaged, but this is not great as cubic and hexagonal ice because it is dissociating when electron is putting on the surface. What other people in the world are doing, people are extensively investigating using this cryo-EM to see this ice, different kind of ice, because previous last 3-4 years, people have published a lot of papers in Nature and Nature Communication about the surface structure of ice and the diffraction of these ices. Now we are at a position we can diffract everything, like we can get a structure, but the imaging is now a problem. And one point, when we are growing clathrate hydrate inside TEM, like which is cryo TEM talus, so we are encountered like most of the molecules, water molecules is forming cubic ice. We are not seeing the THF clathrate hydrate, although we are THF depositing the THF. So one problem with this, I have to analyze the data very carefully, because the electron diffraction data, you don't know the spot is like 0.1 Armstrong inverse is difference, because THF and cubic ice will show the same spot because the diffraction, the dispacing is same for both the molecules. So this is one difficulty. Other than this, I don't think any difficulty is there.
Okay, Soham, to proceed.
Yes, sir. Bijesh, the nice talk. So in your slide 10, you have shown the dependency of substrate in the formation of, like you have shown that actually there is no dependency. But if you see this, the data at 105K, you see for HOPG and gold 111 substrate, these hemicircular rings are coming. But for hydrophobic surface, the fringes are line fringes are coming. So why is it so?
Yeah, actually, I also talked about this during this presentation. Maybe I did not clarify it properly. This is due to, because reflection high energy diffraction is very specific to the surface, the few nanometer, 1 to 5 nanometer. So this, what you are seeing, it is not more than 5 nanometer. And when we are closing the valve, you know, sometimes water is more, sometimes THF is more on the surface. It is not uniform, because in Houston, they are not like two lines. There is only one line for both mixture of THF and water. So in this particular two cases, you will see here the surface is dominated by water. Here the surface is dominated by both THF and water. But in this case, the surface is dominated by purely THF. So this is diffraction, what you are seeing. This is for THF, pure THF crystalline solid. So when we thermally anneal, this THF, obviously, you know, it will dissolve at a higher temperature. So the surface will be different and you will get uniform surface at higher temperature.
But for hydrophobic, it should be reversed because the surface is hydrophobic. So water should be more on the top of the ice layer. And THF.
Yeah. The hydrophobic substrate, it is correct. but we are depositing multi-layer ice. I told 60 nanometer ice.
Yeah.
So once 2-3, it is dependent only if you work on 2-3 nanometer extent.
Okay.
It will work 5 nanometer, but after above that, it is not dependent on the surface anymore.
Okay.
So you can do also pure water ice on hydrophobic surface. So this is just to reminder, it's very low temperature and hydrophobic surface.
Yeah, I know that. Yeah.
not an issue.
And in the previous slides, like you have in rare spectrum, you have shown that there are many components. Like for THF, this ASW trapped THFs are also there in the spectrum at 105 and also 140K. So have you like, is it possible to observe such kind of ASW trapped THF in by this read also? Like, can we
Yes. You can see this figure, HOPG at 105 Kelvin. This is crystalline THF buried in the amorphous solid water. So I was talking just 1 second before why we are facing in talos. You see, the D-spacing between the pure THF crystalline solid is exactly matching with the cubic ice spacing. See, the ring and the second ring and the spot is well matching. So it is typically difficult to differentiate this. But yes, this is THF inside amorphous solid water, crystalline THF. But different type of crystalline, so this is, you cannot tell. It's very spectroscopy can tell you better in the type of environment, in the terms of environment.
Okay. And your read study in the first of the few slides in the result and discussion, you have yes, exactly. So here you are showing that that the very topmost layer, like few nanometer layer you are showing, and the read is scanning the data. So like as you told that it's a polycrystalline ice. So in the bulk ice, there might be some amorphous ice, also a cubic ice in a more dominant way, but with some other ice can be present. The other phases of ice can be present there. So can we differentiate that here in the spectrum?
Yes. This is actually a great question, because people have seen hexagonal ice also in different substrate, but in particularly HOPG substrate, people have observed cubic ice. If there will be a hexagonal ice here, you can see, because hexagonal ice have different XRD pattern. So the ring will come here. In between these two, there will be one ring come. So a different diffraction pattern you will see. But in the case of this HOPG substrate, Young group also observed the cubic ice only till the desertion temperature. But few people have studied in different substrate. They have showed that, okay, cubic ice and hexagonal both are present. But on HOPG, only cubic ice was observed, pure cubic ice.
Okay. And you have not done any concentration dependent study, because we all know this kind of ether, it is possible to make some weak interaction with water. Or if you take some other molecules, for example, they can make some hydrogen bonded interaction. So if we can do some concentration dependent study and take the corresponding read spectrum, then we can actually compare the data. What is your thought about that?
Yeah. This is actually, I want to answer. When I joined this Young group, so he was not first believed that Clathrate hydrate of KH system can form in thin monolayer. I have 3 months, so what I could have done is this much. But I have to believe him that Clathrate hydrate can possible in this kind of system. He was like amazing, like how a structure, like if you see the structure too, see, look at this structure. Other people also can see this structure too. This is a bigger structure and the cages are there. Is it possible? Can it form in very thin monolayer? He also like very interested. But later he told me, Bijesh, you check when we got this data. So he told me to check if there is any THF and water complex is there, because it is possible. So we have also checked that is not possible. Why I was telling you this, because the time was limited 3 months, and first he was to believe that Clathrate hydrate is possible. Then we have done all these stops and this experiment. But yeah, if we have a setup, we can do all this. Or question we can answer.
Okay, and my last question is, can we quantify the amount of Clathrate hydrate by using this data, this read data? If yes, then how?
Let's know, because reads cannot tell you the whole ice. We told it's very specific
Up
to
surface level also.
Yeah, surface. It's very specific to surface. So I don't think, and I don't know we can do it or not.
Okay.
Actually, I don't know how can we do it. Can we do it by diffraction method? I actually don't.
Okay. Thank you. Thank you so much.
Okay.
Anyone else have the question?
Bijesh, nice presentation. This is Ramya here. Am I audible?
Yes.
Yeah. Can you go to slide 9? Maybe we have gone through this before, but it's a very basic question. At temperature 105 Kelvin, you're showing this amorphous water, whereas as you're annealing, cubic ice is formed. Can you explain the basics that's happening here? I would expect the other way around. I mean, if you're actually talking about matter at higher temperatures, this would not
Yes.
happen, right?
This is 105 Kelvin. And
Yeah.
can you clarify your question, like what you
Yeah,
exactly
I
want?
understand that these are extremely low temperatures, but when you compare 105 Kelvin and 140 Kelvin, you see that there is structure in the ice at 140 Kelvin as you're annealing from 105 to 140. So can you explain what is happening?
Okay. So what happened at very low temperature when you deposit some vapors on a very cold substrate, it's called quenching or hyperquenching. So you didn't give enough time to the molecule to get crystallized. So it's just hyperquenched means it will form amorphous solid water, high density. So
Okay.
when later you increase the temperature, that amorphous solid water hyperquench will start to mobile. And
Rearrange
it will get
themselves.
enough time and temperature to crystallize. Yes, it
Okay.
is true that crystallization leads to the exothermic process, and here also exothermic heat also released. But as the temperature is low, we don't quantify that heat.
Okay. Okay, makes sense. Thank you.
Okay, Bijesh, it is probably good to look at some futuristic projects. Something we know from this data that you people have been working on. Hydrates can completely unexpected phenomenon can happen at low temperatures. This is the outcome of this hydrate research. At 10 Kelvin, something happens. Quite unexpected. And today it can be detected by diffraction. You can probably later on in a few years from now, you will be seeing, maybe even today, tomorrow, we will be seeing these structures and morphology is imaged. The hydrate morphology is imaged. All of these are completely unexpected. Very nice. Now think about a little somewhat further. Is it not possible to think about new hydrates? We have been thinking about 3 kinds of hydrates. We have clusters, for example. We have much larger things. We have viruses. Can they form hydrates? What is the limit of forming water cages? Is it only these small cages with small molecules? Now, some years ago, people thought that bacteria or things of this kind cannot exist at low temperatures. Yeah, we proved them wrong. People have detected. I have seen people putting silica shells around bacteria, and the bacteria are still alive. People take these bacterial powders with with these kinds of silica shells around it. Again, coming to the point that completely unexpected things may be possible, and not necessarily from the perspective of the hydrate phases that are known at high pressure conditions. Maybe new kinds of larger cages are possible, and even much larger structures can be buried in them. Do you see such possibilities? You know, now that we have capacity to observe water, we see water along with clusters. You know, cluster is only one example. Anything, you know, if there is the largest, let us say, you know, electron can be diffracted, ions can be diffracted, atoms can be diffracted, meaning atoms also move as waves. Electrons move as waves. Ions move as waves. Then people showed that C60 can move as a wave. Right? Similarly, what will be the kind of largest molecule that can go into a cage? Can a cluster go into? Can naphthalene go into? Can phenanthrene go into? Pyrene go into? Okay, I stop here. Is that, again, I'm asking the question as to what are the frontiers? What are the new questions you can ask? You are a PhD now, right?
Yes. Sorry, this all type of fundamental chemistry you can do, but what is the relevance? The question. Actually, with micro-ED you can do a lot of things, because Horsita also has seen like the process. You can do diffraction of very small crystal, which was not possible before. So that's the reason we can explore new clathrate hydrate, and I also believe that clathrate hydrate several structure exist, because water here has 20 structures, and theoretically it was proven that more than, maybe I'm wrong, 5,000 or some kind of structures can possible. So in hydrate also there are a lot of structures can be possible. Particularly what you suggested, like naphthalene, anthracene, this kind of molecule. They can really form a bigger cages and bigger hydrate, but no one has tried this. We can try. The relevance is also a matter of question.
No, I mean, as far as hydrocarbons are concerned, there is always relevance, because hydrocarbons of any kind exist in nature, under the ocean. It can be under a deep, you know, just as hydrocarbons are present under the earth, similarly, water is also present under the earth. There may be conditions where such hydrocarbons and water are coexisting at high pressures and sufficiently low temperatures. So there is some kind of relevance. I'm certain about that. So,
And I myself believed, I also talked with you, like water also have a different structure, maybe at low temperature, cryogenic temperature, because people have not explored this. Just now, like 4 or 5 years before, people started to see like this kind of imaging, and there are many structures we can do actually in future. Like if all things go.
no, that is one direction. There is another kind of direction of impurities. The other kinds of directions of impurities that you can have. So that impurity is one direction, completely new direction.
Yes, sir. Surfactant. That is a very good direction. Like I was talking with some people, have tried to see what actually really surfactant do, and you can see in micro-ED and imaging what that guy is really doing. So that was a very good direction.
Yeah. Okay. Yeah. So is it possible now to understand new? I mean, you have made, you can understand whether it is formed, etc. Can we learn a little bit more about such hydrates and their properties in UHV conditions? So we have spectroscopy, we have structure, but the next thing is structure and properties, right? I mean, we are assuming that this hydrate is the same thing as the other hydrate. Can we think about or study the properties of such hydrates? I mean, what kind of tools are required to do that? Yeah.
Micro-ED can tell many things. Like I was sharing this charges. Now people are quantifying the charges of different atoms. So this kind of many things can possible in micro-ED.
You see, the moment you have a molecular crystal, molecular material, you ask the question like their core structure. Use structure that gives you properties such as conductivity. That gives you properties. What is a compressibility of this? What is the molecular property is one thing. What would be the solid state property of this? Now, which solid state property will be of relevance? That's also an important question. You know, is it that hydrates are more stronger than ice? Ice, we know, is one of the strongest materials. Yeah. I mean, that's why all the all the glaciers live. They are mechanically pretty strong. But are the hydrates strong? Is it possible? Because in TEM, people study mechanical properties.
Yes, sir.
So I'm just thinking further as to, now Soham is also hearing this, what are the properties that you can have these? Yeah, great. Are we supposed to be making more and more of these clusters, more and more infrared, more and more TEM? Or is there something more? Harshita, this is also relevant to you because people will ask this question, you saw some crystal structure, so what?
Yes, sir. This is a good question, actually. Actually, after study also only can tell, like, now I don't have any answer, particular answer.
Okay, so I have that. Any other question? I don't. Right now, it is as I think through this, these are two fundamentally related things that I want to ask. What is the limit of hydrate? Huh? And so you make it, so what? And then comes the question, okay, you make this, it is yeah, it is useful in etc. etc. You can write some stories about it, like they are useful in flow assurance, whatever. But show it with your own work that what are the properties of this. So C60 was studied. Okay, nanotube, prepared, TEM, whatever. But you showed properties of nanotubes. Like they are strong, they are weak, whatever. They are conducting, they are metallic, whatever. But they're all TEM work, remember.
So I don't have the correct answer right now. Like,
I'm not, of course, you're not probably having answers, but these are pointers. And why am I asking this question? I'm asking this question to everybody. You know, just this that you gave this talk and we had 10 minutes to talk about it. Now I'm keeping my brain alive, right? Active and asking those questions. But you are sitting on this every day.
Sir, I have a thought in this regard. Actually,
Yes, go ahead.
like, yeah, so we all know that hydrate can be formed in very low pressure and very high pressure also. Like, we can put some very high gigapascal or something on hydrate and it can sustain that under the seabed. So it is a pressure absorbent, like it can absorb the pressure or it can sustain under a high pressure. So let's think about some protectant or some armor the soldiers are using to hold the pressure or sustain the pressure of the upcoming bullet, or if bullet is hitting and that pressure can be sustained by a material. So now replace that material with a hydrate. it's cheaper, it's like it's easy to available, easy to make it available, and the hydrate is actually protecting upcoming bullet, high velocity bullet, and then keeping it, staying it as an armor. So I have a thought in this direction, like if we can make a material based on hydrate that can sustain high pressure, also very low pressure, or it would not break up. In this direction, we can think about that.
But Soham, with the kinetic energy, it will not melt. Like the hydrate will not decompose because the kinetic energy will be high.
Yeah.
Also, the bullets will be very hot, right?
I once thought to make bullet with
That
ice. Then I thought it will melt. You just
that's
kill
you are
someone.
saying about the friction, because the heat is generated because of the friction.
No, so when you fire a bullet, there is an explosion from the gunpowder, right? It will heat
Yeah.
up the bullet to a very high temperature.
Yes.
So that's why when a bullet enters the wound around the bullet entry will be always burnt. So that's how much hot the bullet will be. So I think after one bullet, your material will go bad. Maybe even if it can stop one bullet, after that it will be of no use, probably.
Yeah, but collision can be of different kind. Not I have just put an example of bullet, but it can be a collision of different types of materials in different scenario. So might be in a few scenario, hydrate might be useful. It's just a
Cold
proposition.
bullet. I mean, Soham is talking about cold bullet.
Okay.
No, sir.
Uh,
Soham is talking about cold jacket. I talked about cold bullet. Like if you kill someone and then it will melt and all the evidence.
Bijesh, I have one question. Like, do anyone have explored the mechanical property measurement on this hydrates? Like with the AFM or with some other techniques?
Yeah, sir was asking the same question. Like there are very few people have done some kind of mechanical like heat transfer and all this kind of conductance, all this, but that was not explored very like in details. People have not explored.
Okay.
Like the thing is the relevance. What is the relevance? The most matter because hydrate is not stable at room temperature and pressure conditions. So that is one question, and like people have not explored it much.
Very fundamental question. Like, what is the primary condition to make anything to be hydrate? What are the primary conditions? Like something to be a hydrate. What
Our
is the
objective is to expand the conditions.
Yeah. No, like, so what is the primary to understand, like, but since the amino acid, like how the origin of life happened, like in the interstellar medium. So there is amino acid and there is water. So do the amino acid and water will make the hydrates? So I am trying to ask the question in that perspective. So is there any chance to get form the like some hydrate with the water and the amino acid or some protein?
That's
Because
where we have to expand the question in the sense that to what size can we go, right? That's the question. So your molecule that you've chosen is the right molecule.
how I will know, sir? Like that's my question. What is the primary condition to know this is the right candidate for the hydrates?
No, you see, you're putting that kind of a thing, then you are putting this hydrate is nothing but a cage.
Yeah.
We keep thinking that the cage can be only this kind of cage. But is it not possible to have a very thin atomic sheet? Atomic sheet, very big, very big. So this question was asked, and that was the answer was C60. Oh, C60 never ended. It became C540. That also did not end. So if you start thinking about it, there is no end to atomic cages, especially with carbon. Because the cages are very strong. You can make big cages and put Deepak Patel inside that.
But the
I'm saying
okay.
it is possible to think about carbon cages like this.
But there is some limit. The cage will collapse.
Cage may be. I'm saying cage may be. See what we are talking about now, eggshells.
Yeah.
Eggshells you can go and make. I mean, what is the limit of the calcium carbonate cover on it or thickness? You have aragonite or whatever. So you put all your proteins and all that and create shells. You see, how strong is it? I mean, I have seen on egg shells, egg lorry, lorries are transporting eggs. And you can put so much a load on it. My question to Bijesh is from this perspective that, well, is it not possible to make larger cages? So that's a fundamental question that has to be answered. And Deepak's question is, hey, is it possible to look at it from the point of view of biology? Which cages would be relevant to biology? So those are all interesting, very interesting questions that we can address both by spectroscopy as well as by diffraction. My Harshita must be thinking about something, I hope. Okay, so this is one side. The other side of this thing is, as I'm thinking through, this is a cage which is having pressure. You can put pressure. And mechanochemistry is becoming increasingly relevant. Because mechanochemistry is a way to sustainability. We have written several papers long ago on this particular thing, making nanotubes and all that thing in mechanochemistry. Now, is it not possible in your cage doing some mechanochemistry? This guy is in a cage. Now you pressurize that cage. Far more. Anyway, I just left it there for everyone to think as to their projects. Can we look beyond?
I have a answer to Deepak's question. Like,
Please.
yes, Deepak, it's certainly possible to accommodate smallest amino acid, that is the glycine, inside the cage. Actually, I started to thinking about that before. Like, the glycine has all amino acid at this isoelectric point. So if we can take with water and see those things, but specifically speaking, for our instrument, we can't put amino acid because NH2 group is that, so it is like detrimental to our instrument. But amino acid can be, like, smallest amino acid glycine can be put inside the cage. Size is perfectly well. And secondly, like, our perspective is always to put a molecule inside the cage as a guest molecule, but it's not always true, because there is another category called semi-Clathrate hydrate, where the molecule is not always the part as a guest molecule. It can replace the water from the cage and part of the cage also. Like a particular molecule is part of the cage, or it is sharing partly the cage and partly inside the another neighboring cage as a guest molecule. So it's in between two cages, where some part is infused in the cage, and some other part is infused as a guest molecule in another cage. So in that way, if we create some kind of this kind of Clathrate hydrate, a larger size can be accommodated than it's possible in a typical Clathrate cages.
Sir, this mechanochromic project, mechanochromic you told, now we have a microED also there, and Clathrate hydrate is also there. So I was thinking, like, this is a good thing, like if we can pressurize, because people have seen the structures, different kind of ice, 20 types of ice, but people have not seen this hydrate on this mechanochromic. So we can actually do this, we can think about this way, like the changes of the structure, how it is changing.
Yeah, good. Okay, so
So anyone have other question?
I am going to ask Harshita to ask a question.
Bijesh Bhaiya?
Yes.
And the problem is that what we are facing right now for these structures is there is so much disorder in this THF and CH4 molecule. And to solve those things is a major issue which we are facing right now for these structures. So like that, for that, I need a major help because to collect the data and to process it till there, it's fine. But when we have to solve the structure till water cages, still we can do. But when it's come to the disorder part, that is the difficulty that we are facing right now.
This, inside a cage, it is a free molecule.
Mhm.
So
Position is not fixed.
yes, this position is not fixed. So it's a great challenge to the diffraction people also. It's a great challenge.
Because we are collaborating with the Lucas Pelatinus group, but for them also it is a big challenge to fix that position.
No, but
Yes.
there is this point that cages, whatever molecule that is there
Mhm.
is a rotator phase. I mean, the molecule may be in a rotator phase, but it freezes. Like
Yes.
methane, like hydrocarbon, the methyl group is rotating. And the rotation stops. In crystal, generally believe that it is stopped, but it is slightly higher temperature. They are all rotating.
Yes.
So
Or
how
also, sir, another case may be the different cages, the molecule inside, the guest molecule may be in different orientation.
Yeah, that's what I'm saying. So
Yes, sir.
at an instant in time, in a periodic crystal system, every molecule there is in different arrangement, right? Different rotational orientation. So as a diffraction is seeing that that average of that rotating system, but system freezes,
Mm.
and the rotations do freeze. So one of the ways by which this system can be made simpler is to further go down in temperature. To do this, you can now our machine is okay 80 Kelvin. We can do this experiment, make your rotate whatever hydrate at higher temperature, 40, 140, whatever, freeze, go down. For self-assembled monolayers, at 120 Kelvin, if you say octadecane or octadecyl chain, the methyl group rotation freezes at 120. So room temperature, it is rotating. So you get the read or any such experiment, correspondingly, you get the rotator phase only.
Yes. And this is the reason when you go to lower temperature, you will get a more clarity diffraction part.
Yeah.
Bijesh, are there Clathrate hydrates with guest molecules which interact and stay in a single orientation with the hydrate?
No,
Oh,
this is like what you have told is correct. It is in
Mm.
different cases that
But
they might
Bijesh,
be.
if something is inside the cage, they should be bounded. Like some interaction will be there, so they should not free to rotate as frequent as outside.
Deepak, it should not be like that's never that's not always the case ki there should be an interaction. There is even argon can be stored inside hydrates, as we have seen. Argon storage or noble gas storage can be done inside hydrates. So there should be there are no interaction of noble gas with that. So it's not always the case ki there is an interaction between host and guest.
So the degree of freedom outside the cage will be more or inside the cage? Like if any molecule is there, so which will rotate or have the more degree of freedom?
That's an important question, but obviously in gas phase it will be more rotational, but inside cage it is also free to rotate. It depends on the molecular size and the guest size and the cage size. It depends. If methane is there, it will rotate more. If there is a bigger molecule like THF and all the molecule, it will rotate slowly. It depends on the size only.
So another question related to this. What make the your clathrates to be crystalline or amorphous to the host molecule something, or why something is becoming the crystalline and amorphous?
It's a totally different part. Amorphous ice, when we are telling it's a hyperquenched ice. That is totally another story.
There I didn't understand, like when you were saying it was like from amorphous to going the crystalline, but I will expect something which is very cold. It will go first a very order periodic stacking, which will make the more crystalline than the amorphous.
So
When
it
you
is
are
here
doing
to
the deposition, when you are doing the deposition at low temperature, even its deposition will be the more periodic, and it I will expect more crystallinity rather than the amorphous.
Deepak, for crystallinity, you have to give us a little bit time, right? So even our nano clusters, if you don't give much time, it will precipitate out. Amorphous material will come out. Maybe
Among
that's
these
the
are the
case.
very small domain. So I'm thinking like such a small domain, how it can form the multi-domains. Just think about the very nano level, because these are the very small layers, a few layers. So they should be very periodic compared to what we are seeing in a bulk. So everything starts from the periodic to the distortion level. Na?
So it depends on the surface temperature. If you deposit the same molecular vapors at 150 Kelvin, you will get a crystalline ice. But if you will go to lower temperature, what I was telling to Ramya ma'am, that molecule is hyperquenched. Hyperquenched means molecule settled with no time. It didn't get enough time to crystallize. That's
So what is the crystallization, first of all? What is some nucleation where the order periodic arrangement of the lattice? No?
Yes, at lower temperature, molecules didn't get enough time to get this order structure below 120 Kelvin for water ice. If you go below, the temperature is so low, molecule did not get enough time. So to crystallize, it should be reorient, right?
Then I have a doubt. When we put the crystallization, why the low temperature prefer?
Correct.
We don't prefer 120 Kelvin, Bijesh.
No, I'm not telling
One
about the
second.
no.
Okay.
I'm just correlating the temperature things, like
Yeah,
going to 120 and 0 to sometime crystallization we do a minus 20 degrees Celsius. So why we are preferring the low temperature?
Yeah, listen to me. So this is a simple thing. When you take water, when you lower the temperature, it will become ice. When you are taking amorphous solid water, but then you increase the temperature, it is becoming ice. So what you are doing, in case of water, the entropy is high. The molecules are highly reoriented and highly mobile. So you have to lower down the entropy, lower down their molecular reorientation to get crystallized. If you see a molecular simulation, a water ice crystallization simulation, the molecule are freely reoriented inside water molecule. When you lower the temperature, this molecule slow down, and with slow down, it gets structurally ordered.
Because their energy is getting like this kinetic energy is getting slow down. So when that's
Deepak,
why you are when lowering the temperature.
You are just thinking too much. You just take a phase diagram of water.
Yes.
If you go at lower temperature, there will be asymmetric. Sorry, not asymmetric. No, amorphous water will be there in one phase at a particular temperature and pressure.
No, his question is
origin,
good.
like
That origin I'm telling.
The origin.
That origin I'm telling. You need a specific entropy you have to give, mobility you have to give to the molecule, get crystallized. In case of our system, we are freezing it, like we are giving no time to get mobile at 10 Kelvin or 90 Kelvin. But in case of water, liquid water, you'll see, it is already mobile, the entropy is high. So there you are decreasing, here you are increasing the mobility. You understood? When 10 Kelvin to 160 Kelvin, you are slowly increasing the mobility. But where you are going from water to ice, you are slowly decreasing that mobility. So any crystallization, you need to slow down the molecule to get crystallized. That's why in your cluster, maybe you are decreasing the temperature because your molecule is not slow. They are like random. In a bus, if you take 50 molecules and you start running, that 50 molecule will be reoriented. And after a few minutes, when bus stop at the next stop, you will see there are vacant places. The people will reorient itself. Like it's a simple example if we'll take. and they will settle down in a side or somewhere. So that's how
So,
you have to give.
Thank you for the beautiful explanation. Then if I add at that temperature, low temperature where hyperquenching is happening. Now, if I'm in very painfully, I'm introducing the molecules instead of what you actually do, then am I giving enough time for the molecules to crystallize? Do you think that would happen?
No, it's not depend how time you are depositing. It's the surface and the molecule touch, right? It's the time.
Right.
So what time you are talking about?
I mean, you're introducing the molecules onto the substrate, right? For them to get absorbed and deposit. So here, if you're doing it so painfully slow, that molecule touching your substrate, such that when the next one is coming, in terms of concentration and dilution and time, then
That's what I
they will
told.
crystallize, right? Then they will
What we can-
crystallize at 105 Kelvin itself. I mean, you don't have to anneal it to 140 Kelvin to get cubic structure. Maybe at that temperature, you can see crystallization.
No,
Going by your
that's not.
explanation, right? That should happen.
No, that's not how it works actually. It works when the molecule deposit on the substrate. At what temperature the substrate? That temperature defined how speed the molecule quenched.
Yeah, so
Right.
that speed only I'm talking. If you
How you will
reduce the
control the
rate,
speed? How you will control
let's
the
say
speed?
hypothetically, then that should happen, right?
Because
That
I
should
have also
happen.
one hypothetical question.
No. This kind of you can't, like, how it will slow down.
So, you are saying your crystallization depends on the temperature of the surface, right?
So good.
So,
I suppose there is a lot of question. We need to,
oh, time is over. Okay.
yeah, we need to think about the time. Should not lock up.
Okay, I'll catch him later.
Yeah,
Tonight.
interact with people. Well, Bijesh, you have opened up possibilities.
Yes.
What I would like everybody to realize is that there is certain amount of critical thinking that is needed by everyone. Rather critique of one's own work is needed. To what extent, not criticism, critique of one's own work is needed. As to how this is expanding, critique is what? Critique is something that produces new knowledge. In the context of your work and the past work, how is your thought contributing to new knowledge? This makes a better student, a better person. And Bijesh, in that context, I should say that including the last explanation of bus stop and molecules getting the right stop at temperature, fantastic. So you are on that right path. And that is, for me, it is a very highly motivating and satisfactory. Satisfaction is increasing as I see this. The more bus stops you have, the better. Apart from the bus stop model, you have some other models, multiple models to explain the same thing. It essentially tells me that you are thinking about it. The more you think about it, for me, it is a very satisfying thing.
Shall I conclude, sir?
Conclusion, you are going to make the conclusion, Deepak. And so the better conclusion you make of this, then I will also congratulate you for conducting the meeting well. Why don't you summarize this work?
So thank you everyone, and thank you Bijesh for such a nice presentation on driving us to the crystallization and diffraction with the electron micro-LED, electron diffraction as well as infrared spectroscopy. So I have some question which I will ask you after this meeting. So next meeting will be, I will be sharing the link and the speaker. So thank you so much everyone for joining today. I hope everyone enjoyed today's talk.
I really enjoyed. Fantastic. It was very nice. The only thing that I am only unhappy that some people could not join or did not join, or did not find time to join. But my message to everybody is that in this process, you also generate or create value for yourself. You can't attend everything, there are a whole lot of things going on, but we need to at least attend, just as you attend your family wedding, it contributes to your own, well, connections, whatever. Similarly, here this contributes, and the more you ask questions, the great it is. And I would have liked everybody to ask questions. That's the only way for someone to know whether you have some content inside you. And you also know whether you have some content with him. All the very best to you. I'm asking my first year people, I don't see, I see, who am I suppose? Swagata Mandal is here, but I don't see Noorji. I don't see Riswana. Yeah. So the more you are participating in it, the better it is. Madam Mandal, hope you are there.
Sir, I am here.
Very much. Fantastic. Please tell Noorji that I was looking for her. Please tell Rizwana that I was looking for her.
Okay.
Thank you, Bijesh. Thank you, Deepak.
Thank you.
Yes, sir.
Thank you,
Deepak.
everyone.